Good evening. Uh, Good evening, everyone. Welcome to this lecture on social networks. So this is a tutorial lecture where we'll be covering week 8 questions. So week 9 questions will be discussed tomorrow. So we'll discuss week 8 questions from previous iteration of this course. So without any waiting, let us start solving the questions. I'll share my screen. All right, I hope you can see my screen. So let us start with the questions. So just a minute. Just a minute. Um, I'll reshare my screen. Thanks. Welcome everyone. Sorry for that delay. So let us get started with the questions. So question number one is in a social network, if tour guides point people and tourists to tourist destinations, which of the following is correct? So you have four options. Hubs are represented by tour guides and authorities by tourist destinations. Hubs are represented by tourist destination and authorities by tour guides. Tourist spots and tour guides both act as hubs. Tour guides and tourist destination both represent authorities. So in this model of hubs and authorities, hubs form pointers and authorities point resources. So tourist guides, tour guides, they basically act as pointers. They direct you to tourist destinations, which are basically resources. So this is the place where you want to visit. So tourist destination are the resources and tour guides are the pointer. So in this model, so tour guides are the hubs. So tour guides are hubs and authorities are tourist destination. So option A is the right answer for this question. Uh, am I audible? S- someone pointed I'm not audible.
Yes, sir, you are audible.
Okay, thank you. Okay, so moving to the second question. If a Markov matrix A whose eigenvectors and eigenvalues are v1, v2, and lambda1, lambda2 respectively is applied on a vector v repeatedly k times, which of the following is true, considering we keep normalizing the resultant vector after each iteration and lambda1 is the greater vector and k is very large. So let us represent, so v1, v2, v1 and v2 are linearly independent. Therefore, it means that they can act as basis, can act as basis for any random vector. So you have this matrix A and you pick any vector v. Now v can be represented as some linear combination of, let's say, k1 v1 plus k2 v2. So this statement implies that any random vector v can be represented as a linear combination of the two vectors. So therefore, AV can be written as uh, in the following fashion: A into K1 V1 in plus A into K2 V2. Now, if we do A square V is, okay, just a minute. So this can be, we can simplify this up further. So K1 into AV1 plus K2 into AV2. Now AV1 is basically lambda 1 V1 and AV2 is lambda 2 V2. So this is what we get. Now if we multiply, if we look at A square V is basically again A into A1 lambda 1 V1 plus A2 lambda 2 v2, which is k1 lambda 1 into a v1 plus k2 lambda 2 a v2. Now a v1 and a v2 again can be simplified and written as k1 lambda 1 into lambda 1 v1 plus k2 to lambda 2 to lambda 2 v2, which becomes k1 lambda 1 square v1 plus k2 lambda 2 square v2. Now if we re repeat this process for k times a to the power kv, it will turn out to be k1 into lambda 1 to the power k v1 plus k2 into lambda 2 to the power k v2. Now since lambda 1 greater than lambda 2, lambda 1 to the power k would be much greater than lambda 2 to the power k. Therefore, this second term will almost disappear. So, ak to the power v would be k1 lambda 1 to the power k into v1. And if we normalize, then we get ak into v would basically uh, become k1 lambda 1 to the power k v1 by k1 lambda 1 to the power k, which is basically v1. So the right answer for this question would be option A. Ak into v would eventually become v, and if we keep normalizing it, then we'll get v1. I hope this is clear. If you have any doubt, you can ask, or you can ask at the end as well. Okay, let us move on to the next question. Question 3. So what will be the coordinates of the vector 5, 7 after normalizing it to a unit circle centered at origin? So basically what they're asking is, suppose this is your coordinate axis, and let's say this is your circle. Now what they're asking is, find the, let us locate this vector 5, 7. Would be somewhere here. So this is 5 comma 7. So this is 7 and this is 5. And let's say this angle is theta. So they are basically asking us to find what will be the coordinates after normalizing it to a unit circle. So they are basically asking us what is the coordinates of P. Is basically this is equivalent to coordinates of P. So how do we find coordinates of P? So this length is 1 since it is a unit circle. So this length is 1. So coordinates of P are basically, you have cos theta and sin theta. So what is cos theta? So cos theta is basically, if we look at this outer triangle. So let's say your given point is, let's say C, and this is O, and let's say this is D. So cos theta is basically OD by OC. So OD is 5 and OC is root over 5 square plus 7 square. Similarly, sin theta would be CD by OC. So CD is 7 and OC is root over 5 square plus 7 square. So coordinates of P are basically 5 by 5 square plus 7 square and 7 by root over 5 square plus 7 square. So on simplification, this is equal to 0.58 and 0.81. So the right answer is option B. All right, let us move on to the next question. Okay, so what would be the resultant vector when we apply the matrix M on the vector 7, 9, where M is 5, 6, 8, 3. So basically what they're asking is if you multiply 7, 9, what is the resultant vector that you get? So if you multiply 7 and 9, what you get is 5 into 7 plus 6 into 9 and 8 into 7 plus 3 into 9. So which is equal to 35 plus 54 and 56 plus 27. That turns out to be 89 and 83. So the right answer is option C. I hope this is a very simple question. Most of you can easily answer it. So if you have any doubt, you can ask me or we'll proceed to the next question. Okay, so coming to question 5, which of the following is a property of a Markov matrix? So you have four options. All eigenvalues are greater than 1. Smallest eigenvalue is 1. Largest eigenvalue is 1. And all the eigenvalues are less than 1. So the right answer is for a Markov matrix. What is a Markov matrix? Is a matrix where all columns add up to 1. So you have multiple columns in a matrix, so each of these columns will always add up to 1. So in such a case, for such a case, it is seen that the largest eigenvalue is 1. So all eigenvalues of Markov matrix are less than equal to 1. So this option D is not correct because there will exist one eigenvalue whose value is 1, and option D says that all are less than 1. So option D is not right. And similarly, you can eliminate option A and B as well. So the right answer is option C. The largest eigenvalue is 1. Uh, Coming to question 6, so you have been given a matrix. So the question is this a Markov matrix? So like I mentioned, all columns must add up to 1. So let us name this. Let us look at this first column. So the sum of the elements is half plus 1/4 plus 1/4. So on adding, this is 1. Second column, you have half plus half, which is also equal to 1. and third column is 1 plus 0 plus 0, 1 plus 0 plus 0, which is also 1. So this is definitely a Markov matrix. So the right answer is A. Yes, it is a Markov matrix. Coming to question number 7, what
Excuse
values
me,
of
sir.
uh,
Excuse me,
e-
sir.
yeah, yeah, go ahead.
Yeah, sir, I want to ask regarding previous question. Question number 6, definition of Markov matrix model.
Yeah.
In assignment, one last question was asked about the Markov matrix properties. Every sum of every column value of every column is sum of every is one. It means same.
So it being same is not equal. So yeah, you are right. So your answer. So sum of every column, every column.
But in assignment, sir, according to of a Markov matrix, both option must be correct, sir. Statement first, sum of element in every column is same. It means that will be one.
Yeah. So it doesn't mention that sum of that same. You're right that it is same, but it does not mean that it is one. So it is only half the answer. So if you say in a Markov matrix, the sum of elements in a column is the same, that does not make it a Markov matrix. There can be many other matrix whose all the sum
And
of elements is one, is more than one. So it could be two, but they do not become a Markov matrix. So Markov matrix are special matrix where that same number that you're talking should be one and not anything else. So being same is only half the answer. That's why it's not correct.
it is mentioned sum of element in every column is same. Second statement, highest eigen value of a Markov
Yeah.
matrix is one.
So that
Yeah.
statement is correct that highest eigenvalue is one. But the first statement that sum of elements in a column is same, that is only half the answer. So sum of every elements in every column should be one. So that same can be anything, but that doesn't mean it is a Markov matrix. So it has to be one, only then it is a Markov matrix.
And lowest value
Lowest
will
value
be.
so lowest value could be anything. So it depends on the matrix, but the highest value is always one. So if you
If
look,
there
so
if
the
there exists in element of a matrix in column 0 1 by 2 1, it means lowest value will be 0.
go ahead, tell the which matrix. Repeat the matrix again. I'll write it.
If you are taking element of a matrix in Markov model, like for
Okay,
example, one value is 0 and one is 1 by 2 and third is 1, what will
so
be the lowest value?
wait. So you tell me the elements of a matrix. Let me write it down, then I can explain it to you.
Yeah.
Okay,
For
first,
example, if you are taking 0 0
okay, zero. Then
1 by 2,
which side? On the left or below?
you can take, sir, for example, in first column, uh, 3
Okay,
by 3. Okay,
okay.
0 0 1 by 2 1 by 2.
Zero, 1/2, 1/2. Okay,
Yeah, second column is 0 0 1,
okay.
and third one is 1 by 2 0 1 by 2.
1/2, 0, 1
0
by
1 by 2.
1 by.
What will be the highest eigenvalue and lowest eigenvalue of the matrix?
So you can see the highest eigenvalue would be 1. Lowest, it doesn't matter what will be. It depends, varies from Markov matrix to Markov matrix. So there is no guarantee for a lowest eigen value, but for sure one will be the highest eigenvalue. You, I can, if you wait a minute, I can compute what the eigenvalue is, but for a Markov matrix, only the highest eigenvalue matters, because when you do this, Markov matrix are basically used for process like this, a to the power k types. So mostly Markov matrix are used for finding the power. So what will happen is that all this lambda 2 to the power k, they will, if they are less than 1, they will all disappear, and only lambda 1 to the power k will remain, which will basically be 1. So for that is what we only need. We do not need what the lowest values or the intermediate values are. So we can tell for sure that 1 would be the highest eigenvalue. That is for sure.
But according to me, sir, this is not a satisfactory answer in Markov matrix. Some other student were asking during assignment about this question.
Yeah, but the lowest eigen, only the highest eigenvalue of a Markov matrix makes sense, but anything else will not, you won't need it for any practical purpose. So obviously you can find it.
Yeah.
Just give me, okay, so just wait 1 minute, I'll find the eigenvalues of this matrix and tell you. But that depends on like matrix to matrix. So if you change the entries of this matrix, those values will change. But what will not change
Okay.
is that the highest eigenvalue 1. So that will always remain fixed. So that is what we always need. So for every Markov matrix that you take, the highest eigenvalue will be 1.
Sir,
Uh,
sir, excuse me, sir. Sorry, sir,
yeah,
disturbing you. Sir, my question is here. If a examiner is asking lowest value of the Markov matrix in
no
this
one will ask
example.
you. No one will
Yeah.
ask you what is lowest Markov eigenvalue of a Markov matrix, because it doesn't make. So obviously, for a, you can ask a like a in a mathematics course what to find the eigenvalues of a matrix. So for that purpose they can ask. But other than that, for no practical purpose, no one will ever ask you what is the lowest eigenvalue of a Markov matrix. Only the highest eigenvalue
Yeah.
of the Markov matrix matters.
Okay. And there will be no negative value also in column.
That is a positive Markov matrix. In a positive
Yeah.
Markov matrix, it won't exist. But there are also exists negative Markov matrix. But for our course, we will encounter only positive Markov matrix like this.
Yeah. Okay. Just a minute, sir. I want to take one more minute also in question number 4, sir.
Okay. Question
Yeah.
4. Okay.
Yeah. In 4, please scroll up in question number 3, sir, where you were using sin theta, cos theta. As
Yeah.
I think, sir, in this question we can compute directly uh, value of for example, like in the form of a and b in vector values. Okay, a under the root a square plus b square directly.
Yeah.
Can we compute
Yeah.
this?
Same
B
thing.
b
So
upon under the root a square plus b square directly.
yeah, it comes from, so that normalization comes from taking cos theta and sin theta. So what you are telling, you can compute directly by taking the square root of it. I was just showing how
Yeah,
it comes like that. So it first
yeah,
assume it is cos
yeah,
theta
yeah.
sin theta, and then you find they are the
Yeah,
same
sir,
thing.
just I am asking to, for example, during examination, we will have no more timing, for example, to solve all these questions in details, more details. We have to
Okay.
apply shortcut method.
Yeah. So if you apply shortcut method, you look at this option. So
Yeah,
if you just see, if you look, so the ratio, so
yeah,
okay, so xpx and py, so
yeah,
the ratio will always be 5 by 7. So this the denominator, that square root term, will disappear. So the ratio, so these ratio of these numbers will always be 5 by 7. All right, it has to be
yeah, yeah,
for.
yeah,
Now if you check 5 by 7, so 5 is greater than 7, you see in option A the first 0.81 is greater than 0.58. So definitely this cannot be a correct answer. Coming
Yeah.
to option D, same thing, it cannot be a correct answer. Now look at this C and B and C can be correct, means they can be possible candidate. Now check at C. C is 0.18 by 0.58. So you can basically round it off by 0.6. So it would be around 1 by 3. So 1 by 3 is much less, is around 0.33, whereas 5 by 7 is around 0.7. So this is option C will be not near to 5 by 7. So therefore option B is the correct answer. It means you can, by elimination, you can check that option B is closer to 5 by 7. So you just have to do some round off. So I did 0.18, I approximated as 0.2, 0.58 as 0.6. So you get 1 by 3. So it is near 0.33, which is far away from 0.7, which is actually 5 by 7. So therefore option B has to be the right answer.
Okay, sir. Okay, fine. Thank you, sir.
Okay. Oh, okay. Let us proceed to question number 7. So what values of page rank will nodes J, K, and L of the given graph have after the first iteration if the initial values are 1/3 for each node? So let us solve it by points. Let us solve it by two methods. So first is uh, points distribution. Points distribution method, and second one we will do by matrix multiplication. So coming to the points distribution method, so node J, for node J, it receives half of 1/3 from node K. So this is mm, so this is from node K, and this is the only input to node J. So this is equal to 1 by 6. For node K, node K receives half from node, it receives half from node J and entirety from node L. So half from node J, and L gives everything to node K. So it's 1 into 1/3. So basically it is 1/6, 3/6, that is half. And coming to node L, it receives half from node J and half from node K. Basically, it remains 1/3. So this is the point distribution. So the right answer would be option B, 1/6, half, and 1/3. Now let us look at this problem from matrix multiplication point of view. So the corresponding Markovian matrix M for this network would be, so okay, let us do it like this. We have this matrix. The first row represents J, second K, and third L. So the first uh, element represents the share of J. So node J distributes its points to 0 points to itself, half to K, and half to L. Node K distributes half to J, 0 to itself, and half to L. And L distributes its entire point to node K. So, okay, so L distributes its entire point to node K. Now we multiply the existing initial eigen, so initial points that were allocated. So initial values are 1/3 for each. So if we carry out this multiplication, what we get is 1/6, then half, and then 1/3. So this is the same as you get from the points distribution method. So basically they are equivalent techniques to find out what the page rank will be. And eventually on convergence, so what will happen on convergence? On convergence, page rank would be equal to the eigenvector of M. So corresponding to eigenvalue 1. So it does not depend what the initial point distribution you start out with. So here they are equally distributing 1/3, 1/3, 1/3. So even if you did not start off with the equal distribution of 1/3, the ultimately on doing this multiple times, the page rank will basically be the eigenvector of M corresponding to the eigenvalue 1. So just from this matrix M, you can tell what the page rank will be. So this is question number 7. Oh, okay. Someone is asking to explain this question again. So where should I explain the question from the beginning, or can you write it in the chat box? All right, I'll explain from the beginning itself. So you have this given network, and okay, so you're talking about method 1. So you have this given network. So how is page rank calculated? Page rank is calculated by, so every node, you assume every node in this graph has a certain number of points initially allocated to each of them. Could be like gold coin. So let's say J has some initial gold coins, K has some initial gold coins, and L has some initial gold coin. So what in the next step, what they do is J is connected to L and K. So what J does is it equally distributes its gold coin to K and L. So it has, let's say, 10 gold coins. So it gives 20 gold, 10, 5 to K and 5 to L. Similarly, K distributes half to J and half to L. And L, as you can see, only gives to K and not to J. So the entire gold coins that L has goes to K. So gold coins are the initial point values of these nodes. And so that is how page rank is calculated. So you carry on this iteration multiple times and ultimately it will converge. So how this point distribution method works is, so initially J had 1/3. So J receives 1/3, half of the points that K has. So, and it does not receive anything from L. So that is half of 1/3 is 1/6. So this becomes a new point for J. K received half from J. So half from J is half of 1/3 from J, and half from, and the entire from L. So L gave 1 into 1/3. So adding half into 1/3 plus 1/3 will give you half, and L receives both from J and K. So J gives half of its points to L, and K gives half of its points to K. So basically half of 1/3 plus half of 1/3, it remains 1/3. So that is how after one iteration you get these values: 1/6, half, and 1/3. So these are the new points, and you repeat the iteration with these new points. I hope that is clear. Okay, so let us proceed to question number 8. So, all right, so this is question number 9. So will a page rank graph with the below adjacency matrix converge? So the question is, so you have the adjacency matrix, so how will the graph look like? So the graph is somewhat like this. You have node, so let's say node A, node B. So these are the nodes A, B, A, B. So basically they have self loops. It means A is connected to A and B is connected to B. So what happens? The points of A, whatever points A starts out with and whatever points B starts out with, it will remain the same. So the page rank will ultimately will show no change. Page rank will, let us say, A started with PA and B started with PB. Page rank will remain PA, PB through all iterations, because they are not distributing. No distribution happens. No distribution of points. Therefore, it will converge. So the right answer is option A. Yes, it will converge. Choose the correct, coming to question 10, choose the correct option based on the given statements. So you have applying a matrix on its eigenvectors only changes the direction of the eigenvector, and eigenvector of a matrix are linearly independent of each other. So you have a matrix A, and if you multiply its eigenvector V, so it will become lambda V. So this basically means scaling V and no change in magnitude. So applying a matrix on its eigenvectors only changes the direction of the eigenvector. So this statement 1 is wrong. It does not change direction. Right. So no change in uh, direction, and only scaling is basically changing magnitude. So the statement 1 is incorrect. Statement 2 says eigenvectors of a matrix are linearly dependent on each other. This is also not correct. They are linearly independent. Therefore, both the options are incorrect. So both statements are incorrect. So option D is the right answer for this question. Okay, someone has written something in the chat. See, like I mentioned before, statement one is partially true. So if they are telling that statement one is correct, so because they are same, that is partially true. So I have no problem with statement one being correct, but that does not that is not the complete picture. So if you give me a matrix where if I take a 2 cross 2 matrix with, let's say, 1 1 and 0 2, so here also the sum is 2, and it means that sum of every column is same, but this is not a Markov matrix.
But sir,
So
second statement is Markov model, Markov matrix. Second option.
the second option
That,
is correct.
yeah, that was the
Second,
definition of the Markov model.
yes, second highest eigenvalue is 1. So statement 2 said that highest eigenvalue is 1. So that is correct. But sum of every column is same is only half correct. So if they are considering it as true, then it's all right. But it does not always mean it is all not always true for a Markov matrix.
Okay, sir. No issue.
Yeah.
And we have asked about examination pattern also, sir, from NPTEL team, but no response from their side.
Okay, so like previous year's question, I do not have any access to the previous year's question. So you have
I
sent me a
I
mail.
I have mailed you, sir, also.
Yeah,
Dr. Roshanlal, yeah, from
I
MIT University, Noida, NCR, Delhi.
so I have forwarded your mail to the NPTEL, the instructors of, so instructor
Yeah,
did not reply to me as well. So
but we have not received any single reply till now, and we will appear in examination also.
okay. So whoever, so for this that you sent in the chat box, who sent you this reply? So did you contact the same people for the exam pattern as well?
No, sir, only to NPTEL team. We, for example, like if I want to ask about any question, sometime they reply also, but sometime they not responding.
Yeah, but uh, I also don't, so I am not in direct contact with the NPTEL team regarding the examination. So that's why I won't be able to help you in this matter. I do not have any extra materials as well for this course. So whatever you have, I also have the same set of materials.
Final examination will cover all content from a video lecture and discussion,
Yeah,
tutorial sheets like and so on, or any other study material need to.
no,
Uh,
I think that
uh,
will be enough. Lecture materials will be enough.
okay, then there should be no issue, as I think I am doing this course additional, and I am also professor here in MIT University Computer Science Engineering Department, and I am doing this course only research purposes also, sir. My MTech student are doing work on in this area
Okay, okay,
in social engineering, science social network.
okay.
So as I think some student have enrolled for their credit transfer purposes also. And one student is asking about some helping also. I have seen that message also.
Okay.
Yeah. So if any concerned person which can help in this regard about the pattern of the examination, that will be beneficial for all student, not only for me. This is
Okay.
optional for me.
Okay, I'll write to the instructor once again. So if they will reply, I'll forward you the message.
Yeah, okay, sir. No issue.
Okay.
And we are getting more what which you are delivering, and we have explored more things. That is very nice, sir. And
Okay.
this
Thank you.
is compliment for you also from our side.
Okay. Thank
Uh,
you.
session are very good, all no issue.
Okay.
But sometime we have some queries, they are not responding.
Yeah, I actually like I am not associated with the team, so neither do I get paid for doing the session. So it is like I do a voluntary, like I learn with you people. So I am just voluntarily doing this TA session so that I learn about this course as well. So I have so they do not directly contact have I do not have any direct communication with them as to how the
Yeah,
pattern
yeah.
all.
Okay, okay, I know, sir. No
Yeah.
issue. And some student are asking about a recording session. In
Okay.
a recording session, you can find out in your course which announcement about course, ask a question progress, and you will see at the bottom problem solving session. You will go on problem solving session, and you will download your Excel sheet, and then you can go for a particular session. Okay, if a student is listening me, so I have explored all these things, sir. No issue. If any
Yeah.
student can share, can if they want to ask some other queries also, so you can see all recording session previous. Okay, go there and click on the link, and you can see. For example, you have delivered today, sir. Next day we can see again many
Yeah.
times. Okay, yeah, no issue, sir. Yeah, thank you, sir. Thank you. Thanks a lot.
Yeah. Yeah.
Yeah, thank you, sir.
Yeah. So if anyone else has any other questions, can you can ask.
As I think, sir, it's okay for today. It's enough.
All right. So if no one has a question, I think then we can close today's session. And tomorrow week 9 questions will be discussed in the same time by a different TA. And again, we'll meet next week. So the if you have no doubt, you can start leaving the session.
Okay, thanks a lot, sir. Thanks a lot.
Yeah.
Hello.
Uh, yeah. Go ahead.
Sir, I unable to access the recording of the session. I tried now.
Uh,
Not get
okay,
this.
I'll share the sheet link with you. Wait, just so this current session is not yet present because I'll have to upload this recording, but till previous weeks you can find. So I have sent you a Google sheet. So this same sheet you can find in that course web page as well. So if you check this sheet, you will find that it contains the YouTube video links for the lectures, and the lecture materials are given in this presentation folder. So can you verify it once?
Yes, sir. I get. Yes.
So this lecture will be uploaded like in half an hour. You can see this lecture. I'll upload it. You can check tomorrow maybe. But other lectures you can check it uh, till week 7. It is already uploaded.
Sir, where I get updated sheet is after this session.
So this sheet will update itself. So if you click on this link, it will keep updating itself. If you just refresh it, it will update. So otherwise in the course web page, you can find this sheet as well. So if you go to the course web page, in the course web page, in the live session section, I think there is problem solving session. So
Okay.
uh, just a minute. Yeah, so if you go to the course web page, there is this problem solving session is there, and there you will find this sheet.
Okay. Sir, can you share the screen? Means what you're doing. Means step of the.
Okay, 1 minute. Just me log in. I'll share. So just give me a minute. Okay. So if you go, okay, let me share the screen. You can see my screen, right?
No, sir. Not visible.
I'm sharing my entire screen.
Yes, yes. Visible. Yes.
Okay, so here if you go down here, this live session books, live session problem solving session.
Yes.
You, you so if you click, you will be directed. So you click here to view the problem solving lectures. If you click here, you will get this sheet, and you
Yes, sir.
can.
Yes.
Alright. So this is the first block is from my side, and the second block is from the other TA. So you can check out her lectures as well. So these are her
Yes.
YouTube links, and the top ones are mine. So you can choose and select whatever you wish.
Yes, sir.
All right. Okay.
Sir, this sheet is only available on this website or
Yeah.
app as well. In app
No,
as well.
I am not aware whether it's available on the app or not. It's available on the website. That's all I know.
Okay.
I,